Okay, can everybody see this all right?
Yes.
Okay, and I guess you can hear me as well. Okay, so yeah, I'd like to thank the organizers for having me here to give my talk. I'm really excited to talk to you about using cathodoluminescence for nanothermometry and thermal transport measurements in semiconductor nanowires. And this is particularly interesting to me because it combines two fields that often don't communicate with one another, cathodoluminescence and nanothermometry. Okay. So nanoscale heat control is becoming increasingly important. So this shows the power density in microchips as a function of time, and you can see that there is an exponential increase in this power density as circuits get smaller and smaller and smaller. And so that means the same amount of heat that's generated in a 100 nanometer transistor is now generated in a 14 nanometer transistor and still has to be conducted away. And so that leads to very large temperature rises in these very small structures. Temperature can have a very large impact on microchip performance. For instance, for this particular inamp, you get over a 200% change in input bias current, for instance, over the operating temperature of this device. Temperature can also have a large impact on photonic structures. For instance, nanowire lasers, they show a change in their emission wavelength as a function of temperature. So this is why if you want to have very stable or well-operating microstructures, nanostructures, temperature control is very important. A problem is that as materials shrink, this affects their thermal conductivity properties. So at nanoscale dimensions, you start to see phonon modes being blocked, you get more boundary scattering, and these things in combination with other factors lead to a general decrease in the thermal conductivity. So there are a number of different methods for measuring temperature and thermal conductivity on the nanoscale. There are many, they're not all listed here. This is just a subset. So some of the highest spatial resolution methods generally involve optical near-field microscopy, scanning probe microscopy, or looking at shifts in the plasma resonance in eels, for instance. Drawbacks for these methods, while they do have very high spatial resolution, they involve scanning probes, which can be very slow and cumbersome to use, or they require, in the case of TEM type measurements, very thin samples. For measuring thermal conductivity, a relatively fast method is time domain thermal reflectance, which uses pump probe with lasers. So while this is fast and it's good for measuring nano layers of structures, it has poor spatial resolution because you're limited by the diffraction limit of light. Another method for measuring thermal conductivity of nanowires in particular is this thermal bridge method, which involves using resistive heaters and resistive thermometers to measure temperature fluctuations across this device. And this, of course, involves a lot of fabrication. So this method that I'm going to talk about involving cathodoluminescence is relatively fast, has pretty good spatial resolution, and involves pretty minimal fabrication. So the samples that we decided to measure are these gallium nitride nanowires that are about 7 microns long and 150 nanometers radius. They're grown by our co-authors with selective area sublimation etching. More details about that can be found in this paper. These wires are very high quality, so they actually exhibit lasing modes under optical pumping. So in theory, nanowires of this radius should start to show a decrease in their thermal conductivity due to a decrease in the mean free path. So bulk gallium nitride thermal conductivity can be up to 220 watts per meter Kelvin. Theory predicts slight decrease, and previous experiments have shown actually that there is much greater decrease than what theory predicts, but the error bars on this measurement are rather large. So we thought this would be a really great sample to test kind of our thermal conductivity measurement techniques. So if you haven't heard about it, cathodoluminescence is light that is emitted when an electron impacts a material. So cathodoluminescence can come from a number of different sources. So in metals, it comes from a different source in general than in semiconductors. So we're looking at semiconductor cathodoluminescence, and it primarily comes from band gap emission. So an electron comes in, loses energy to bulk plasmons, which excite hot electrons, which then excite electron hole pairs, which then combine radiatively and emit band gap emission. So it's very similar to photoluminescence, but with higher spatial resolution. So here is a gallium nitride nanowire in an SEM. And this is a cathodoluminescence map. So what we're doing here is you park the electron beam at each of these pixels, and at each pixel you sum up all of the photons that come out. And what we noticed is when we measure this nanowire with very low current, we get a spectrum that looks a lot like this red curve here. But when we use a high electron beam current, so around 70 nanoamps, and we park this electron beam at the center of the nanowire at 5 keV, so most of the energy is being absorbed in this nanowire, we see a shift in the band gap, a red shift in the band gap. And we realized that this must be due to heating of the nanowire. We realized that we could use this band gap shift to measure the temperature. And this is not new. So there's this Varshini phenomenological equation that describes the band gap shift in semiconductors with temperature. So this occurs for most, if not all, semiconductors, gallium arsenide, silicon. Sometimes the shift is blue, sometimes it's red with temperature. But these parameters are very sensitive to the material and how the material was grown. So it's important to do a calibration to properly fit this equation. So we put our sample on a cryo stage in our SEM and measured with a very low current. So with a low current, we're not heating our nanowires. And we just change the temperature and measure how the band gap shifts. And so we get this calibration curve, and we got calculated about a 6 Kelvin temperature resolution. So then we take the data from the previous slide and at each pixel find the peak emission wavelength, use our calibration curve to turn that into a temperature map. And we see roughly a 500 Kelvin temperature rise in our nanowires under 70 nanoamp illumination. And our temperature resolution, we believe, is primarily limited by doping uniformity. So these nanowires are not completely uniformly doped. And so there is a small shift in band gap due to doping. But so we're estimating 6 Kelvin. So there are a lot of kind of cool things that we can do with this. So if we use an electron beam at low current, you can measure you can just probe a system without heating it. So for instance, if you have some sort of circuit and you want to look at the Joule heating in the circuit or other sources of heating, you can probe that circuit with a low current in situ to see what's happening. You can also generate thermal profiles by simultaneously heating your structure with the electron beam and then using that same electron beam as a probe to measure temperature, which is what we do here. So we have an increasing electron beam current on our nanowire and show an increasing temperature rise. So if we take this image and just take a crosscut through this wire, let me explain. This is a gallium nitride nanowire suspended across a copper TEM grid with a hole in it. And we deposit platinum on either end to heat sink this nanowire so that the temperature is fixed at either end of the nanowire. Anyway, so with this image, we show temperature versus position, and we can fit this curve with a model to extract the thermal conductivity. And the model that we use is this thermal circuit model, which equates circuit characteristics to thermal characteristics. So voltage is analogous to temperature, current is analogous to heat flux, etc. So we can build a kind of circuit for our 1D nanowire, fit this, and then extract thermal conductivity that way. The one drawback to this method is that the thermal conductivity or the thermal contact resistance must be negligible, which is not always the case in these wires. So we came up with another method to measure the thermal conductivity where the thermal contact resistance is not important. So here we just heat sink one end of our nanowire, and we scan the electron beam along the nanowire and measure the temperature at each location where the electron beam is parked. So we measure temperature versus distance, and from the slope, we can extract the thermal conductivity. Again, we use a similar circuit model. The drawback to this method is that you must know the heat flux very well. So you calculate this heat flux by, you know the current, you can measure the current through a Faraday cup in your SEM, but you don't exactly know how much energy is being deposited in the wire. So we can estimate it by Monte Carlo simulations, figure out how much is being backscattered. But this has some error bars. So the next method that we worked on doesn't have, it's not as important to know the heat flux in the nanowire. So here it's an alternating current method. We use an electrostatic beam blanker in our SEM. So here we have two parallel plates, and the electron beam goes through these parallel plates, and you have a waveform generator with a square wave signal, and it basically just deflects the electron beam. And so we can get up to 5 megahertz while keeping our square wave signal square. So here we park our electron beam at the end of our nanowire, and then measure the cathodoluminescence that comes out. So we use a spectrometer that's rather slow, so it's measuring the average cathodoluminescence when the electron beam is on. So at low blanking frequencies, the wire has enough time to heat up all the way. And so when the electron beam is on and we're seeing cathodoluminescence, the average temperature is high. At high blanking frequencies, so faster than the thermal time constant of the nanowire, the wire just doesn't have enough time to heat up. So we get a lower average temperature in our nanowire. And we see this in experiment. So this is just cathodoluminescence counts versus wavelength. And we see a red shift in our emission spectra at lower frequencies, meaning at lower frequencies, the wire is able to heat up more on average when the electron beam is on. So next, we measure this temperature as a function of frequency, and we see very clearly when our frequency is faster than the thermal time constant of our nanowire. And we can analytically solve what this curve should look like for a 1D wire with a periodic heat input at one end, and at one end the temperature is fixed. So we fit this the data with this function, and we can extract the thermal conductivity in this way. And the nice thing about this fit is that we don't need to know anything about the heat input into the wire, because that fit is not correlated at all with the thermal conductivity we extract. So to compare all of our results, we have first our DC bridge method, we have our DC slope method, and our AC method. The DC slope method has this advantage over the first method I talked about because the thermal contact resistance isn't important. And this final method I spoke about, the knowledge of the heat input isn't important compared to these other two methods. And we measured the same wires using these two methods because they could use the same geometry, and we got very good agreement between the thermal conductivity. So I will mention that these wires had very uniform doping. If the doping in the nanowire, some of them was very ununiform, and in that case, a lot of our thermal models no longer apply, so the results don't agree as well. So what we found was that our findings agreed with previous experiments that the thermal conductivity seems to be lower than that of theory, than what theory predicts for nanowires of our radius. So in conclusion, I showed cathodoluminescence thermometry on these gallium nitride nanowires with good spatial and temperature resolution. I spoke about 3 different thermal conductivity measurements demonstrated, and we saw a size impact the mean free path of phonons in our gallium nitride. And in the future, more work could be done on more quantitative phonon studies, doing in situ temperature measurements in circuits. We can look at other semiconductors, we can look at surface scattering of phonons, etc. So I would like to thank my co-authors for this work, others at AMOLF who have helped me, and of course all the funding agencies. And I would like to thank you all for listening and ask if any of you have any questions.